Hello everyone. This week we will cover Module 7 of Chem 1. We will discuss acids and bases.
You are probably not yet aware, but many of the foods we consume and the household products we use to clean our homes can be described using the concept of acids and bases. Acids and bases have several unique physical properties. Acids taste sour, will change the color of an acid-base indicator, and can be strong or weak electrolytes in aqueous solution. Examples of acids are the oranges, which contain citric acid and tannic acid found in tea. We can use a litmus paper to determine if a solution is an acid based on the specific change in color of the paper. On the other hand, bases taste bitter, feel slippery, will also change the color of an acid-base indicator, and can also be strong or weak electrolytes in aqueous solution. Common household products that are basic include antacid, which we take when we have hyperacidity, hand soaps, which we use every day, and ammonia, which is used for medical purposes. Many scientists have attempted to describe acids and bases throughout history. Antoine Lavoisier was the first scientist to give a formal definition of an acid. According to him, a compound that contains oxygen makes a solution acidic. In fact, he named oxygen from the Greek words oxys, which means sour, and gens, which means born. Oxygen literally means acid maker. On the other hand, Humphrey Davy described acids and bases differently. He showed that it was hydrogen, not oxygen, that gave acids their unique properties. Several scientists have since proposed more detailed explanations of what makes a substance an acid or a base. They include Svante Arrhenius, Johannes Nicholas Bronsted, Thomas Martin Lowry, and Gilbert N. Lewis. Currently, there are three definitions of acids and bases that are widely accepted. These are the Arrhenius theory, the Bronsted-Lowry theory, and the Lewis theory. Each of these theories have limitations that are addressed by the other theories. Knowing all of them will give us a better understanding of acids and bases. Let's start by discussing the Arrhenius theory. According to Arrhenius, an acid is a substance that produces hydrogen ions when added to water. When hydrochloric acid is added to water, the hydrogen atom dissociates from the chlorine atom. The free hydrogen then bonds with a molecule of water to form the hydronium ion. Note that free hydrogen, or H+, is an unstable form of the hydrogen ion. The proton in H becomes attracted to the lone pair of electrons in water's oxygen atom, thus forming H3O+, or the hydronium ion. Many references still use H+ to represent hydrogen ions in solution, but H3O+ is the more accurate representation. However, H+ is used as a simplified way to represent hydronium ions. Arrhenius further classifies compounds based on how many hydrogen ions they can release in a solution. Acids that release one hydrogen atom that can form ions are called monoprotic acids. An example of a monoprotic acid is nitric acid, which has only one H in its molecular formula. Acids that release two hydrogen atoms that can form ions are called diprotic acids. An example of a diprotic acid is sulfuric acid, which has two H atoms in its molecular formula. Acids that release three hydrogen atoms that can form ions are called triprotic acids. An example of a triprotic acid is phosphoric acid, which has 3 H's in its molecular formula. Here are some examples of acids that are commonly used in our daily lives. If you have used muriatic acid to declog your drain pipes, you used an impure form of hydrochloric acid. If you use vinegar when cooking, you are using ethanoic acid, also known as acetic acid. Sulfuric acid is used extensively by the fertilizer industry to make fertilizers such as ammonium phosphate and ammonium sulfate. It is also used to make detergents and insecticides. Now let's go to Argenius' description of a base. According to Argenius, a base is a substance that produces hydroxide ions when added to water. So when you see hydroxide ions in the product of a reaction, this is an indication that the solution is basic. Before we proceed any further, let's look at the elements of a reaction. We represent chemical reactions in text in this format. In a reaction, the molecules or atoms on the left side of a reaction are called reactants. They are the ones that potentially separate to form other compounds or other ions or polyatomic atoms. The atoms or molecules on the right side of a reaction are called the products. They are the result of new chemical bondings that form from the reactants. The arrow represents the direction of a reaction. Note that here, the reaction has only one direction. Later on, you will notice some reactions have arrows pointing to opposite directions, towards the product and towards the reactants. In this case, we call these reactions as reversible. Reactions that are unidirectional are called irreversible reactions. Here are some common bases that we use in our daily lives. Sodium hydroxide is the main component of liquid sosa. It has the same corrosive properties as muriatic acid. That is why we also use sodium hydroxide to declog drain pipes. Calcium hydroxide is a component of mortar, which we use in bricklaying. Now let's go to the next theory. The Bronsted-Lowry theory defines an acid as a substance that donates a hydrogen ion and a base as a substance that accepts hydrogen ions. In this example, ethanoic acid releases its hydrogen atom, which is accepted by water. The water then becomes a hydronium ion. We learned in the Arrhenius theory that hydronium ions make a solution acidic. In our next example, ammonia accepts a hydrogen atom from water to form ammonium ion. The water becomes the hydroxide ion. We know that hydroxide ions in a solution make it basic. Going back to the first reaction with ethanoic acid acts as an acid here. And water acts as a base. However, in our next reaction, we know that ammonia is a base, so water here is reacting as an acid. When a substance reacts as both an acid and a base, we call it amphoteric. Bronsted-Lowry further classifies acid-base products into two types based on a conjugate acid-base pairing. A conjugate acid forms from a base reactant. A conjugate base forms from an acid reactant. Let's look at this reaction to identify the conjugate acid-base pairing. In this reaction, HCl is the acid and H2O acts as a base. Water accepts a hydrogen from HCl to form a hydronium ion, and the chlorine is released as an ion in the solution. We know that hydronium ion makes solutions acidic. We refer to it as the conjugate acid of water. On the other hand, the chloride ion that was released from HCl is referred to as its conjugate base. An acid reactant has a conjugate base product. A base reactant has a conjugate acid product. Let's look at the next example. Here we have ammonia, which we know is a base, reacting with water, acting as the acid. The ammonia accepted a hydrogen ion from water, forming an acid product, ammonium ion. The water molecule donated a hydrogen, creating a base product, hydroxide ion. So the ammonium ion is the conjugate acid of ammonia, and the hydroxide ion is the conjugate base of water. Let's practice identifying acids, bases, and their conjugate pairs in these four reactions. First, let's look for compounds or ions that we already know as an acid or a base. Hydronium ions are acids, hydroxide ions are bases. So, in letter A, we can label this as an acid. In letter B, we can label this as a base. In letter C, we can label this as a base. If the compound or ion is on the product side of the reaction, we label it as a conjugate. So this is the conjugate acid and this is the conjugate base. If this is the base, then this must be the acid. Okay? So we know that ethanoic acid is an acid, so this must be the base. If this is the conjugate acid, then this one must be the conjugate base. And the same for reaction B. If this is the conjugate base, then this must be the conjugate acid. We know that ammonia is a base, so in this case, water is acting as an acid. So remember, an acid will have a conjugate base. The conjugate base is what is left of an acid that has donated its hydrogen ions. A base has a conjugate acid, which is the resulting compound when it has accepted a hydrogen. So let's go to letter C. HCN donated its hydrogen to hydroxide ion. So this must be the conjugate base or whatever was left of that reaction, which makes water here the conjugate acid. In this reaction, we see that hydrogen bromide has an H to donate. So this must be the acid, which makes this the base. So when hydrogen bromide donates its hydrogen, what's left of the reaction is the bromine ion. So this must be the conjugate base, which makes the carbonic ion as the conjugate acid. So there you have it. Just remember that an acid will have a conjugate base pair and a base will have a conjugate acid pair. Ions that are positively charged tend to be acidic. Ions that are negatively charged tend to be basic. Here are some examples of common acid-base pairs and their conjugates. Once you become familiar with these molecular formulas, you will have no problems identifying which is the acid and which is the base. Finally, we go to Lewis' theory. Lewis defines an acid as an electron pair acceptor. In this reaction, boron trifluoride reacts with the fluoride ion to produce boron tetrafluoride ion. We can show the Lewis dot structures of this reaction to get a better understanding of the reaction. Here we have an electron pair of the fluoride ion that is donated to boron trifluoride. Since boron trifluoride accepted this electron pair, it is considered an acid. According to Lewis, a base is an electron pair donor. In this example, we have ammonia reacting with hydrochloric acid to form ammonium chloride. We can illustrate this reaction of donor-acceptor using the Lewis dot structures of the reaction. Acids and bases can also be classified as either strong or weak depending on how they behave in a solution. Strong acids and strong bases have the same characteristics. They completely dissociate or ionize in solution, forming strong electrolytes, and their reactions are faster. An example of a strong acid is nitric acid. An example of a strong base is lithium hydroxide. Weak acids and bases also have the same characteristics. They do not dissociate completely in solution, forming weak electrolytes, and their reactions are slower. An example of a weak acid is carbonic acid. An example of a weak base is ammonia. Note that in these examples, the strong acids and bases have a unidirectional reaction arrow, whereas the weak acids and bases have a bidirectional reaction arrow. A unidirectional reaction arrow means that once a strong acid or a base is added to water, all of its molecules dissociate in the solution. There are no reactants left, only products. A bidirectional reaction arrow means that the reactant or reactants do not completely dissociate in the solution. Some of the original reactants remains undissolved. The periodic table of elements can be used to help us determine whether an acidic or basic molecule is a strong or weak acid or base. In general, acidity increases from left to right and basicity increases from right to left along a period. Acidity increases down a group and basicity increases up a group. How do we know that an acid or base is strong or weak? We can put numerical values for a solution using the concept of pH. pH is defined as the measure of the strength of acidity or basicity of a solution. It is expressed as a scale of numbers from 1 being strongly acidic to 14 being strongly basic. We use a formula to calculate pH. It is the negative log of hydrogen ion concentration. Note that the brackets around the ion indicate concentration, or the amount of that substance in a given volume of solution. Let's do a sample problem to practice calculating pH from a given concentration of hydrogen ions. In our first problem, we are asked to find the pH of a 0.0025 molar concentration of hydrochloric acid. We know that hydrochloric acid is a strong acid and it completely dissociates in water to form hydronium ions. So, we know that the concentration of hydrogen is 0.0025. Using the formula for pH, we can write the equation as the negative log of 0.0025. First, we determine what is the log value of 0.0025. Using a calculator, we determine it as negative 2.6. If we multiply this to a negative value, we get a positive. So, the pH of this solution is 2.6, which makes it a strong acid. So, in the next problem, we are asked to find the pH of a solution which has an hydrogen ion concentration of 1 times 10 to the negative 4 molar. So using our formula for pH, we can write this as the negative log of 0.0001. Okay? So first we need to calculate the negative log value of our concentration. Using a calculator, this gives us a negative 4.0. So a negative multiplied with a negative gives us a positive value 4. So the pH of this solution is 4.0, which makes it still acidic.
The pH scale can be used to arrange the pH of common household solutions. For instance, the liquid drain cleaner or liquid sosa that we use to declog drains has a pH of about 14, which makes it the strongest base in the pH scale. Bleach has a pH of about 13.5. Seawater with a pH of 8 is considered slightly basic. On the other side of the scale, milk, urine, and saliva are considered slightly acidic. Coffee is acidic with a pH of 5. Lemon and vinegar are more acidic with a pH of 2. Battery acid and hydrochloric acid are the strongest acids among these solutions, with a pH of almost 0. A solution with a pH of 7 is considered neutral. Pure water is a neutral solution. And that ends our lecture on acids and bases. In this lecture, we covered the 3 most well-known theories regarding acids and bases, and we had a brief discussion about measuring pH. The deadline for submission of Module 7 activity worksheet will be posted in Google Classroom. Instructions on how to submit the requirements are written in the module. Thank you for listening.